Wonderful. I'm Jessie Herbert with We Are Montana in the Classroom at the University of Montana, and thank you for joining us for Brain Awareness Week. I want to introduce Kallie Moore from the Paleontology Center at the university within the Geosciences Department, and she's got some fun stuff for us today to explore, so thank you for being here. Thank you, Kallie. I'll let you go.
All right. Good morning, everyone.
Conference recording has started.
Oh, there we go. All right, we're official now. So yeah, my name's Kallie again. My job on campus is I'm a collections manager. So what that means is I'm kind of like a fossil librarian. I keep all the fossils organized and accessible. And today we're going to talk about paleoneurology. So just to give you an outline of what we're going to try to get through today, we might not get to the activity, but you guys could do it on your own. I'm going to give you a little bit of background. So what is a fossil? What is paleoneurology? And why study it? Why is it important? Then I'm also going to go through some examples. I'll show you some different types of paleo brain techniques, and then look at some samples, the Oreodont and the T-Rex. And then the activity if we can get to it. But I don't know. There we go, perfect. So what is a fossil? Can anybody give me kind of a basic textbook definition of a fossil?
Bone that's been identified? No, that's okay.
Petrified?
A bone that's been petrified? Yeah, that's one thing. The one that I like to use is the preserved remains or indications of ancient life. So this could be anything from bones, like you guys said, all the way to tracks and trails, gastroliths, coprolites, so fossilized feces, that happens. So we give an arbitrary date of anything older than 10,000 years. It's kind of the end of the Ice Age. Most of the megafauna went extinct by then, and they're usually found in sedimentary rock. So sandstone, limestone, those sort of rocks. They're formed via burial, and you need to slow or stop the decay process. So the quicker you can bury something, the better, and the more likely you'll have it preserved. But you also can have, not only with burial with dirt or mud, you could have tar, for example, at the La Brea tar pits, preserves bone very, very well. Amber, so tree sap, so like on Jurassic Park with the little mosquito on the inside of the amber nugget. So we have all different types of preservation for fossils. So again, we're talking about fossils and paleontology and not archaeology today. So no human artifacts or anything like that. So we'll be talking way, way back in the fossil record. So what is paleoneurology? What do you think this is the study of?
Brain?
Brains, yes, brains from the fossil record. So the study of brain evolution by analysis of brain ENDOCAST to determine endocranial traits and volume. So that mainly means an ENDOCAST is the cast of the hollow portion of the skull. So everybody's brain, your brain, my brain, an elephant's brain, pushes on the inside of the brain cavity, and it creates impressions on the inside. And so we can look at blood vessels and nerves can be preserved, the wrinkles of the brain can be preserved, and this can happen naturally through natural processes. So you have a skull and the brain cavity is filled in with some type of mud or something, and we'll actually look at an example of that. You can have man-made, so a researcher using resins or clay to fill that brain cavity and look at what the brain would have looked like. And then digital is really what we use now in paleontology. So we CT scan skulls to look at that space. So again, these are formed when those pressures on the inside of the skull create impressions on the walls of the brain case. So this doesn't tell us anything about like the number of neurons, neuron density, anything about the internal structure of the brain. It only shows us the external portion of the brain. So if you want to think about it, the skull is kind of like the jello mold over here, and our brain is the jello cast that comes out of the jello mold. So here's a few different types of endocasts. Up at the very top, we have two endocasts here. These are man-made. One's from Homo erectus from about 1.5 million years, and this bigger one here is from a Homo sapien that's about 115,000 years. Then we have this guy over here. This is an old world basal canid. So what that means is this is a dog from Eurasia that's at the very, very base of the dog family tree. And this guy, you can see here, this is a natural endocast. So the teeth and everything are over here. Those are the teeth along the bottom. And then this area here would be the brain cavity. The brain cavity is gone. It's eroded away, or some researcher flaked it away to get down to this natural endocast. Then we also have a CT scan here behind me, kind of. So again, this is what researchers are using currently and most often. The larger skull is from a short-tailed possum, and this bottom little guy here, this is really backwards, is from a 190 million year old mammal called Hadrocodium. So the pink portion is the brain area, the inside of the skull, and the reddish pink area here is just highlighting the olfactory region, so the smelling region of the brain. So why would you study a paleo brain? Anybody have an idea of why paleo brains are important, or why would we study them? Anybody? Anybody? Well,
we don't bite, I promise. It's totally...
I can't get to you. You're miles away. So why would you study a modern brain?
To better learn the way it functions?
Exactly. Yeah, so that's one of the big reasons. So behavior is tied to brain evolution. So the behavior of an animal is very, very closely intertwined with the brain. Another way we can study brains is looking at the brain evolution across fossil groups, actually. So here I have a nice little time is on the bottom, volume, so how big the brain is. And it goes all the way from some really, really old hominids over here with, under 500 cc brains, all the way up to us Homo sapiens and Neanderthals. So this is really important for human evolution, for example. And then they also represent potentially large amount of phylogenetic data that we don't normally look at. So normally when we're trying to group different species of extinct animals together, all we look at are the bones and teeth mostly. So this gives us a whole nother line of evidence of how closely or distantly related these fossil groups are. I'm just going to touch on this one really quick because it's awesome. This is the oldest brain known, this guy here. How old do you think this brain is? The oldest brain ever. 200 million years? I think I heard that one.
Mm-hmm.
Yep. Okay,
Yeah.
this one's actually 520 million years old, so a 500 million year old brain. It's from southwest China, from the Xinjiang Formation, and I'm not even going to attempt to say this name. You guys can practice at home later. And it's from this ancient arthropod. The preservation of this guy is absolutely amazing. So here's the tail area, then the body region, and the little head area, and then the brain is all the way up here. This is an up-close picture of the brain, and then we've drawn some structures over the top, and then some great reconstructive artists kind of made the illustration here. So these things had crazy three-part brains. They looked a lot like modern insect and crustacean brains, which makes sense because they were arthropods. Crustaceans are also arthropods. So I just threw this in here. And this is soft body preservation. So we don't have the whole brain preserved or the brain cavity preserved. What we have is more of like a carbon film, like a squish of the brain. And the elements of the brain are preserved on the rock. So any questions about paleo brains up to this point?
No.
Okay. So how many of you guys, just wondering, have ever found a fossil? You can just raise your hand. I found a fossil. Any of you guys ever found a fossil?
A couple of them.
Yeah. Do you know what type of fossil it was?
No.
No? That's okay. If you ever want any of your fossils identified, you can contact me via email with some images of it. You can just snap them with your phone and email them with me. Email them to me, and I can try to identify them over the internet. So I have a specimen here that I'd like to show you.
Okay, here we go.
We gotta change the camera here.
I do, and then we have to. I'm sorry, it's really blurry, but it'll be not so blurry in just a second. There we go.
Okay. So this guy here is an oreodont skull. So I'll talk to you a little bit more about what an oreodont was. But what I mainly want to show off here is the endocast. So this is a natural endocast. So sediment has come into the brain cavity here and filled in the empty brain cavity. And what we're left is that you can kind of see the ridges right here of the back of the brain. It would have come up in here, and this would have been the nasal olfactory region of the brain up front. So I'll walk you around. These are the eye sockets here. This is the nose. Here are the teeth and the top of the roof of the mouth. All of this in here is actually sediment. The green stuff in here is sediment. When we prep fossils to keep these zygomatic arches intact, a lot of times we will leave the sediment in this hollow area to add strength so the specimen doesn't break as quickly. But yeah, this is a really great natural endocast. So we'll switch back.
Perfect.
Green screen.
Ah, here we go. Then we have to move her a little bit. It's coming, you guys. Here it comes. Ready, steady, go.
So an oreodont, this is a reconstruction of what we think oreodonts look like. These are from Turtle Cove in Oregon, and you guys saw that the sediment is green. Well, it really, really is green. This is a picture from the area where this specimen is collected. It's absolutely gorgeous, I think, with the green clay stone. So a full skeleton would look kind of like this guy here. There were so many different types of oreodonts. They were very, very widespread, but they disappeared about 4 million years ago, and we're not exactly sure why they disappeared. But anyways, we saw the ridges of the brain that look kind of like this here. So all these little lines are just different areas of the brain that researchers were looking at. So this is from a publication. The next thing we're going to look at is T-Rex's endocast, and you don't have to change it. I'll just hold this
Okay.
up here. So this is an endocast. This is a man-made endocast from T-Rex, and I've got it a CT scan version blown up here, and we're going to kind of walk through this. So can anybody identify the olfactory region? So I've got my specimen pointed the wrong direction. There we go. So the smelling region of the brain. And you can describe it using any of these symbols, the Roman numerals, the letters, anything like that. Where do you think the smelling region of the brain would be?
I'm just going to zoom in on you really quickly, and then, actually what we can do too is if you want to walk up a little bit towards the camera, then we'll have a little bit better vantage.
Yeah, so that guy is on its side. Let me move mine.
So is it, okay, so now it's oriented the same way that the picture is. So, the smelling region, what do you guys think? Using those letters or numbers up there.
The front of it?
Go back. Yep.
Tell them.
The front?
So with the letters, which letters in the front here do you think represent?
You guys read them. You can't really see the letters.
Oh, okay. So the front. Sorry. All right. So you guys are correct. This is the olfactory region of the brain. So the front of the brain. Gosh, this is annoying.
I know, there you go. It's really hard to be on a green screen because everything you see is backwards. And so you want to point one direction and then it just goes opposite of where you think you're going to point.
All right, so let's look at the hearing area. So maybe the color there, I will give you a hint. There's a color change for the hearing area.
Is it red?
Red.
Like the reddish pinkish color? Yeah, so it's right here. So reptiles have a different hearing setup than mammals do. Mammals, we have these tiny little bones on the insides of our ear, our middle ear bones. Reptiles don't have that yet. They have what's called a labyrinth, a cochlear labyrinth. And so they had tubes on the inside of the skull that helped amplify the sound. All right, now vision is kind of tricky, but where do you think vision would be? Do you think it would be closer to the olfactory region or closer to the hearing region?
Hearing.
Yep, it's a little closer to the hearing. So it's kind of right.
Welcome. Thank you so much for joining us for Brain Awareness Week. I'm Jessie Herbert with We Are Montana in the Classroom, and I wanted to introduce Kallie Moore. Here, she's with the Paleontology Center at the University of Montana with the Geosciences Department, and has a lot of fun stuff planned for you today. So I'm going to turn it over to Kallie and enjoy. Thank you, Kallie, for being here.
Yeah, thank you. All right, good morning, everyone. Like Jessie said, my name's Kallie. I'm the collections manager, so what that means is I'm like a librarian for fossils, so like a fossil librarian. I keep all the specimens in order, organized, safe, and accessible. So before we get started, who finds fossils interesting? Who likes fossils? Just raise your hand. Nice! High five kid up front. First hand raised. Yes. So has anybody found a fossil? Yeah, of course. Good. So does anybody know what you found? Can you ID your fossil for me? Yeah, go ahead.
I'm pretty sure it's something of either an arm bone or a leg bone. Pretty sure.
Oh, sweet. Very cool.
Yeah. Well,
Anybody else find a fossil that they can identify? Or knows what it is? Well, if you don't know what your fossils are, you guys can contact me via email and just send me a picture, and 9 times out of 10 I can identify just from a picture in an email. So if you need my contact information, we can get that to you. So did anybody bring a fossil in by any chance? No? Okay, just checking. Every once in a while somebody might bring one in. All right, well, let's go ahead and get started. This is the basic outline. This is where we're going to go today. I'm going to do a little background. So what is a fossil? What is paleoneurology? I guess I forgot to tell you today we're looking at paleoneurology. And why do we study it? Why is paleoneurology important? I'm going to show you some examples. There's different types of paleo brain, so a hint, and then Oreodont skull, and then we'll talk about T-Rex. Then hopefully we'll have enough time to do kind of a visualization activity to try to get you guys to realize how big T-Rex was and maybe not so much how big his brain was. So what is a fossil? Can anybody give me a basic textbook definition of what a fossil is? Okay. Yeah, go ahead.
Go ahead.
It's a remnant of past animal organisms that is now rock.
Yeah, really good. So my little favorite definition is preserved remains or indications of fossil life. So we can have bones, we can have teeth, we can have shells, we can have the exoskeleton like of a trilobite, petrified wood, for example. Then we can also have trace fossils, though. So this would be the indication of life. So tracks, trails, footprints, burrows, gastroliths, stomach stones, coprolites, so fossilized feces. Those are types of trace fossils. But pretty much so everything under the sun can be fossilized, all the way from single-cell organisms up to like T-Rex. We give an arbitrary date of 10,000 years or older. So anything that's considered 10,000 years or older is a fossil. Anything younger than that can be considered a subfossil or modern. And they're usually found in sedimentary rock, but we'll talk about some exceptions to the rule. So they're formed by slowing or stopping the decay process. So the faster you can stop the decay process, the better. And this is usually done by burial, so mud or something going over the top of something that's dead. However, we can have tar preserved fossils, so like at the La Brea tar pits in California. We can also have amber, so pine sap encapsulating a little insect. I just saw a manuscript that came out last month that they've actually found lizards inside of amber. So very rarely does anything vertebrate preserve in amber. And then you can also have like the permafrost in Siberia, so a frozen fossil. So right now I just heard that they found a domesticated dog, a puppy, a little pupsicle as I like to call it, that's about 12,000 years old. A domesticated dog that's about 12,000 years old. And cave lion cubs have been found. Mammoths, all different shapes and sizes of mammoths, are preserved frozen in the permafrost. So not always with burial, but usually. So again, we're talking about paleontology and not archaeology. So I won't be discussing any human artifacts or arrowheads or anything like that. We'll be talking about paleontology today. So what is paleoneurology? Can anybody guess what paleoneurology is? The study of what? Yeah, go ahead.
It's a study of the brain of a fossil, maybe, comparing it to a living being.
Very good.
And trying to find there.
That is basically it. So the study of brain evolution by analysis of brain endocast to determine endocranial traits and volumes. So endocast, that's kind of a key word here. So that's the cast of the hollow of the interior portion of the skull, so the brain cavity. And this can be done naturally with sediment, so mud or sand filling in the brain cavity. It can be done by man-made, so researchers using clay or resins to fill the brain cavity to look at that ancient space. And then what we normally use today is digital. So we can take CT scans of the brain case and look inside without having to break apart the bone. So they're formed when the brain creates pressures, and then those pressures create impressions on the inside walls of the brain case. So I like to use the Jello mold and Jello. So the Jello mold over there is like your skull, and the Jello cast that comes out of it is your brain. So what we do is we look at this hollow space, and everybody's brains have almost like a fingerprint of your brain cavity has like a fingerprint of your brain on the inside of it. So every single one of you have a slightly different brain fingerprint on the inside of the skull. One last thing I do want to mention, so these can show different regions of the brain. They can show blood vessels where nerves come out, but they can't show us anything about the internal structure of the brain. So how many neurons did they have? What was the neuron density? That doesn't tell us anything from the ENDOCAST that we look at. So here's some examples of different types of ENDOCAST. So this top one up here, the one on the far side, is an endocast of Homo erectus, about 1.5 million years old. And then the larger brain right here is from a Homo sapien, so about 115,000 years old. So very, very old. Both of these are man-made. They're made with like a resin or plaster from the skulls of these ancient humans or hominids. I have a natural endocast over here. This is from an old world basal canid. So what that means is like a very, very old dog at the base of the dog family tree that lived in Eurasia. About, let's see, how old is this guy? Anywhere from 5 to 2 million years old. So to walk you around this brain, these are the teeth of the skull. This would be like the nose, kind of the eye socket here. And then this is the brain cavity. Now, the the bone of the brain cavity has either eroded away naturally or researchers have removed it to look at this natural endocast. So here's a side view, and then this is the top view. So you can kind of see the ridges of the brain here, different areas of the brain. This is probably the olfactory or smell region of the brain. It's usually up front. Then this is what we mostly look at today. If we don't have the natural endocast, we use CT scan. So the top bigger skull here is from a short-tailed possum, a modern short-tailed possum. This little skull down here is from a 190-million-year-old mammal named Hadrocodium. And what the researchers are highlighting, the pink area is the brain, and the reddish pink area is the olfactory region. So again, that's smelling region. So we use CT scanning a lot now when we study ancient brains. So why would we study ancient brains? Why even look at them to begin with? You guys can raise your hand, shout out some answers.
To the evolution of our brain, the history of it.
Yes, exactly. So one is to understand the behavior of extinct animals. So behavior and brain evolution are very, very closely tied. Then I think what you mentioned is brain evolution across fossil groups. So this one's very important for human evolution. And I've got some brains up here. So time is on the bottom, volume over there. So how much volume these brains take up. So from like the very, very early hominid about 6 million years ago, just under 500 cc's of volume, all the way up to us Neanderthal, well, not us Neanderthals, us Homo sapiens and the now extinct Neanderthal. Upwards of 1,500 cc's. So we can look up the evolution across fossil groups of just looking at their brain. And then the other way we can use these paleo brains is that they represent a potentially large amount of unexplored phylogenetic data. So usually when we're trying to group animals by likeness, or I guess unlikeness, we look usually at their body fossils, so bones and teeth, to group them by similarities. But we can also use the brain, the ENDOCAST, to look at the change over time and to see if something might not look very similar, but their brains are very, very similar. So I'm going to switch gears just slightly from ENDOCAST, so actually looking at the space of the brain cavity, and just highlight the oldest brain ever. How old do you think the oldest preserved brain is? How old do you think this little smear of a brain is?
2 million?
2 million? Way up.
10
Wait,
million?
10 million? This one is actually 520 million. So a 500 million-year-old brain is right up here in the head region. So I'll walk you through this fossil. This is kind of the head up here, the body, and down into the tail. This is a close-up of the brain. This is with some structures laid over top, and then this guy here is the reconstruction of what we think it might have looked like. So this specimen was found in southwest China. It's part of the Xinjiang fossil locality, and they have a surprisingly complex 3-part brain, and it's very, very similar to modern arthropods like crustaceans and insects, which makes sense because these guys were an ancient arthropod, so their brains haven't changed that much in a long time. This is preserved as like a carbon-rich film, so the brain has actually been squished, all the water has been pushed out gradually, and what we're left with is almost like a carbon film of the brain, so it's not like the ENDOCAST that we've been talking about. This wasn't a fluke, this wasn't just some crazy researcher saying, hey, that's a brain. 7 different fossils were found with the same structures. And these were found using a scanning electron microscope, so a very, very, very high-tech, high-powered microscope that fires electrons at the specimens to look at the structure of the specimen, which is very, very cool. So any questions up to this point about fossils or the fossilization process or paleo brains in that matter? Okay, good.
Oh, no worries, sorry.
So I have a specimen here for you to look at, and it is an oreodont. And so the live creature looked like this guy here. This is a little reconstruction. Here's what the skeleton looks like. And I have a natural endocast here. We got to change the view around a little bit.
Oh, hold on. I know it's a little fuzzy. We're going to take care of that. There we go.
All right. So here's my skull I have to show you today. This skull came from Oregon, and I'll kind of walk you through it to get you orientated. This is the nose area, so the nasal is right here where they would breathe through. The teeth are all along here. Here's the eye socket. This is the cheekbone, zygomatic arch. This would be the back of the skull, where the spinal cord would come out, is right here. And then this glorious feature is the brain. So this is a natural endocast. Sediment has actually filled in the brain case and has left a natural cast of what the brain would have looked like. So I think if I turn it to the side a little bit, you can kind of see the ridges of the brain here. So we actually have some structure preserved. Now, all of this green stuff that you see, like up here, over here, that's all the sediment. And sometimes when we prep out skulls like this, we'll leave the sediment in the hollow regions to help keep structure to the skull so it doesn't fall apart or break.
Okay, here we go.
All right, we got to switch back.
Gotta switch back here. There it goes.
All right, so the sediment that was infilling this skull comes from this amazing locality in Oregon called Turtle Cove. And this is actually what it looks like. The rock out there is this brilliant bright green color. I think it's just glorious. It's so pretty. So these oreodonts were distantly related to camels, we think. They were very, very widespread across North America. Here in Montana, we probably have, 10 different species of oreodont. And they were sheep-sized, hog-like, four-hoofed toes. So they had 4 toes, but little hooves on the end of them. They were very, very strange. There's nothing quite like them today. And they mysteriously go extinct about 4 million years ago. We don't really know why. There was a little bit of some climate change occurring about that time, but nobody has really found the smoking gun for the oreodont. The other specimen I have that we're going to look at is T-Rex. So I brought with me a T-Rex endocast, and it's pretty, it's small. Let's just say that. It's kind of unspectacular. It's not very big, as you can see. It's pretty small. But I have a CT scan of the endocast from T-Rex, and this was created in 2013. So I'm going to walk through the brain, and you guys are going to help me identify different parts of the brain. So we'll start with the olfactory region, because I've kind of mentioned it a couple of times, and I've showed it in a different slide. So where on this brain, so this is the front, and this is the back, this is top, this is bottom, and if you can read these labels, you can just read out which label you think correlates with the structure that I'm asking for. So where do you think the olfactory region of T-Rex's brain was? Yeah, go ahead, you can.
OB, ONS, that part of the brain area.
Yep, very good. So OB actually stands for olfactory bulb. So that's where the smelling region is for T-Rex, which it makes sense. It's the closest to the nose region. So now what about hearing? Where, maybe what color, or again, how about the one, you, I don't know if that's left or right, the far one to me. Yeah, you.
CVCM.
TVCM.
C.
Oh, that
C.
top part? Not
Yeah.
quite. It's not that one.
It's the CAR.
CAR. This one right here? No, not that one.
L-A-B? Lab?
Yes, lab. That's it. So that reptiles hear a little different than we do. We have 3 inner ear bones, which create the noise and the vibration that we pick up into our brains. Reptiles don't have that. They have this labyrinth, L-A-B, that's what it stands for, a labyrinth of tubes that amplify the sound for them. All right, so vision is a tricky one. Vision is tricky. Where do you think vision? Do you think it would be closer to the nose or closer to the ear?
Closer to the ear.
Closer to the ear.
Yep, it is. It's closer to the ear. So it's kind of right here. Now this is a trick question kind of because even researchers don't exactly know where the optic region of T-Rex's brain is. We know that this here, this number 2, Roman number 2, is actually the optic nerve that comes out of the brain. So we know that that's there. And usually the vision area is between the cerebellum here and the hearing area. So I just kind of arbitrarily put this is probably where the optic lobe of T-Rex's brain is. So this tells us a lot about the habits of T-Rex. So although this brain is small in my hand, if we compared this brain to all other non-avian carnivorous dinosaurs, do you think this would have been a big brain or a small brain? Raise your hand for big. And raise your hand for small. Raise your hand if you didn't raise your hand at all. Okay, so this is actually a big brain. It had relatively the largest brain of all adult non-avian dinosaurs. So avian dinosaurs, so dinosaurs that kind of were on the trackway to birds, had actually really big brains. They were definitely on the scale of about as big as a modern bird's brain if you compare body size to brain size. So now let's talk about sense of smell. Do you think that T-Rex had a good sense of smell?
Yes.
Yes, yeah, he did. Very good sense of smell. What would T-Rex use his sense of smell for, you think?
That is very debatable.
Yeah, they thought he might be scared.
So maybe scavenging, maybe hunting, smelling prey. But what else do animals use their sense of smell for? It's not all food related. What does your dogs do every time you take them for a walk?
Smelling for hormones.
Yeah, exactly. So marking their territory, smelling other people's territory, and also smelling to figure out who's ready for mating. So, again, T-Rex devoted a large amount of the brain. I mean, all of this area here is devoted to the brain. All of this is for everything else, or devoted to smelling. All of this is just the rest of the brain. So again, scavenging, hunting, we now know that T-Rex was opportunistic. I know that there was, Jack Horner came out and was like, oh, T-Rex could only scavenge. Well, now that we've got all this brain information, also T-Rex weighed like 9 tons. That's a lot of meat that this creature had to eat to keep his energy levels up, to even keep going. Living on a straight carrion diet is not enough for T-Rex. That's not good enough. And so we now know that he scavenged and he hunted, which makes sense. I mean, if you think about lions in Africa, they can scare away smaller prey or smaller predators from a prey site, a kill site. They can hunt themselves. They can do about anything. So T-Rex being the largest predator ever, practically, definitely you can do a lot. So what about vision? Or let's see, do I go sorry, I have some notes here.
Okay.
Sense of smell and then hearing. So do you think that T-Rex had a good hearing? He could hear pretty good? Maybe.
Probably average.
Maybe. Do you think he focused on low frequency sounds or high frequency sounds?
Low frequency.
Exactly, he did. These guys, oops, don't read that last one. They used low frequency sound. So do you guys know of any other animal that uses low frequency sound? Yeah.
Elephants.
Exactly. Elephants. Did you have another one?
Yeah, blue whale. Or is that
Blue
high
whale.
frequency?
Yeah, so they are using low frequency to go through water, and then T-Rex and elephants are using low frequency to go through air. Low frequency travels very, very far. And so we think that T-Rex could have maybe talked to another T-Rex over miles of distance. All right, so now we're on to vision, and this one was kind of the reason why we now think that dinosaurs could hunt and they could scavenge. So, T-Rex sight. So in Jurassic Park, T-Rex, you can't, he doesn't see you if you don't move. Do you think that's correct anymore?
No.
No. We'll talk about that a little bit more. So we now know that T-Rex could use rapid head movement of the eyes and the head and the neck. So this guy could use its head rapidly to look around and scan for prey or to track prey. I have this image up here just to show you where the brain sits in the skull. And this is looking at smell in particular. So the air would have come through the nostrils. The heavier air would have gone down into the lungs. But the smaller odor molecules would have come up into the upper nostril and to the olfactory bulb of the brain. All right, so Jurassic Park, I kind of ruined the surprise already, but there's this scene in Jurassic Park. So I guess first, how many of you have seen Jurassic Park? Just raise your hand. Yes, most of you have seen it. Good. So here's the scene. T-Rex flips over this car. Dr. Grant comes out with a flare, and he's waving it around. He's trying to get T-Rex to follow the flare. So we now know that T-Rex had pretty good eyesight. He could see its prey. He could track its prey. So Dr. Grant would have been dead pretty fast. But if he would have actually made it past this scene, we get to this scene where T-Rex takes a huge whiff of Dr. Grant and Lex here. So now we know T-Rex had a really good sense of smell. So even if he couldn't have seen them clearly because there was water in his eyes or something from the rain, he definitely could have smelled them. And again, they would have been dead very quickly. So T-Rex, Jurassic Park would have been a little bit of a shorter movie had T-Rex, had we have known the brain functions and behavior of T-Rex. So I have a cool little video here. It's a walkthrough video of the T-Rex display at the University of Montana. I took this with a fisheye lens, so you'll notice when it starts that the edges of the case kind of look bowed a little bit. And that's just from the lens that I took it with. So I'm going to tell you a little bit more about this T-Rex in particular. This was found in 1997 near Fort Peck, Montana. So this guy is nicknamed Peck's Rex. It's about 65% complete. I think we have most of the right side of the body. A lot of the left side of the body was eroded away, washed away. T-Rex itself was about 13 feet tall at the hip, so now we know that T-Rex walked out kind of balanced in his legs down here. So 13 feet tall at the hip, about 40 feet long altogether, nose to tail tip, and weighing up to 9 tons. So the 9-ton estimate is from Sue. Sue is the largest T-Rex ever known, ever found. But this guy is not the size of Sue. So it's probably anywhere from 7 to 8 tons, but still, that's pretty big. It had a bite force of about 13,000 pounds of pressure can push down in one of these bites. So that's the biggest bite of any land creature that has ever lived. That's like an elephant sitting down on you. That's the type of pressure that it's creating. 75% of the world's T-Rexes ever found are found here in Montana, and that's because the sediment, the late Cretaceous rock that T-Rex is found in, is at the surface in an arid environment. It's much easier to find fossils when you can see them lying out on the floor than having to look through a jungle and getting through all that vegetation. And the very first T-Rex ever known to science was found in Montana by Barnum Brown in 1902. So we have a lot of history here in Montana with T-Rex. Okay, we can switch back. Perfect. Here we go. So here's another little diagram up here to kind of help you orient. This is a normal, average human adult male. And then T-Rex and Triceratops, probably one of his favorite prey organisms that he would have eaten. So now I think we have just enough time to quickly kind of look at this. So I think what I'll have you guys do is have one person pace out the length of your room. So just counting how many steps it takes to go from one wall to the other. Yeah, that was quick. Thank you, sir. Wow, 7.5 steps. So that's about 14 feet. So T-Rex's stride, just one stride length from T-Rex was about the length of your classroom. T-Rex himself was 12.3 meters long, so that's about 40 feet long. So if you guys had a chance to get a measuring tape and maybe go out to the hallway to see if T-Rex would even fit in the hallway of your school. Then we also I have some other measurements up here. So an average height of a human, worldwide average height, is 1.73 meters. So that's about 5'8.5" is about worldwide average for how tall we are. The length of our brain, so from the front of our brain to the back of our brain, is about 16.7 centimeters. And then the nose, from our nose to the back of the skull, is about 21.6 centimeters. Now, when we look at T-Rex, it's a little different. We actually have to do average length of T-Rex and not average height. And then length of the brain, so this whole brain, is about 20 centimeters long. And then tip of the nose to the back of the brain, or back of the skull, so tip of the nose to the back of the skull, is about 1.5 meters. So 1.5 meters is about 5 feet long. So if this guy were to eat me, just like my ankles and my feet would stick out of his mouth. That's a really big animal. So a fun way to visualize this is using tape. You tape out your brain. Okay, my brain is 7 inches or 20 centimeters long. And then from there, put another length of tape out for the length of the skull. And then put another piece of tape out to the tip of the tail, and look at the body size versus head size versus brain size. And you can do this for both T-Rex and humans. So I can send this slide to you guys if you want to actually look at it on the floor, because it's pretty amazing how big T-Rex was and how small his brain was. But again, T-Rex wasn't writing poetry or doing taxes or calculus or worrying about how somebody felt at the end of the day. T-Rex was instinct driven. It's eating, sleeping, and mating, pretty much so. So you don't need a whole lot of brain power to do your basic instinct driven behaviors versus us humans, who we've got awareness and we make all this stuff, we have technology, so our brains are much bigger in comparison. So does anybody have any questions or comments or anything like that? Yeah.
How exactly do you get the endocast out of the skull? Like, how does that work?
So very good question. I'll just use this guy. So best case scenario, there's a natural endocast. So we can just study the natural cast from the inside of the skull. So a lot of times the endocast is much, much harder than the surrounding bone. And the bone will erode away or can easily be picked away and destroyed by researchers wanting to look at the endocast. Now, if you had, let's say, a paleo human brain, and we just had the brain cavity, just this top part of the skull, we could actually fill it with like clay or plaster or something like that. It's very destructive. So researchers try to shy away from man-making an endocast nowadays. We much prefer to use CT scanning because that allows us to look inside the skull without having to bust open the brain. So you digitally slice through the brain cavity and look at the structure versus having to crack open the brain cavity. So, any other questions? Yeah, go ahead.
When Jack Horner came out with his theory about how T-Rex was a scavenger and not a predator, what were your thoughts on that?
I thought it was ridiculous. I was like, really? You're pigeonholing the largest carnivore to ever live to being just a scavenger? I never jumped on that bandwagon. I always thought that, you know, as I call him the king of the Cretaceous, he could have scared a small pack of raptors away from a kill site and stole their meal. He could have smelled a dead carcass somewhere and walked to it and ate it. Or using his 25 miles per hour of speed and 13,000 pounds of bite force could have easily taken down a young or sick hadrosaur, triceratops, something else. So it seemed very unfair to just say, oh, it's just a scavenger. This guy couldn't have hunted. What? No. And now we know with that brain study. So again, that brain study came out, let's see, what was it? In 2009. So the study came out in 2009. So now we know a lot more about the behavior of T-Rex than what he knew when he decided to just say that without a whole lot of evidence.
That is exactly what I thought when that came out, because why would such a large predator like that be only confined to scavenging?
Exactly. Yeah. And so again, now we know that T-Rex had rapid vision. So he could move and tilt his head very quickly, kind of like if you think about like a hawk or something perched up on a tree and looking for little field mice. Their head and neck moves incredibly fast. So we think that T-Rex probably had anywhere vision quality in between a modern reptile and a modern bird. So that's pretty good still. He could have definitely seen you moving and tracked you. So again, it's fun when new science comes out because it gives us a much greater understanding of these ancient animals for sure. So any other questions?
My teacher just was wondering what kind of classes are offered for this at U of M.
Oh yeah, so you can't major in paleontology at the University of Montana, but through the geosciences we do offer a few classes, up to 4 different paleo classes. So we have history of life, which is what it sounds like. It's the history of life going all the way back to about 3.5 billion years, all the way up to humans. Then there's paleobiology, which is looking much more in depth at paleo life on this planet. Then we have a couple of seminar classes for upper level undergraduates. So we've taught a paleo techniques course where you learn different types of prepping and also how to inventory specimens into a database. So half of the class is up in our prep lab and the other half of the class works with me down in the collections room learning collections management. And then sometimes we'll have a seminar class with a topic. So a past topic has been mass extinctions and recovery events. So what causes the mass extinction, and then how does life recover from that mass extinction. That can change though, depending on need, what people need to know about paleo. So sometimes we could teach a index fossils course if sedimentologists wanted to learn more about the index fossils that they can use to relative date the layers that they're working in. So we've got about 4 different paleo classes. I also work heavily with volunteers, so I have anywhere from 2 to 15 volunteers each semester that work in the collection with me on various collection projects. Right now we're working on Cambrian trilobites that were collected in the 1930s and 40s and never formally inventoried into our collection. So nobody knows they exist outside the students and myself that work in the collection. So we're trying to get those digitized right now. I'm assuming that collection is about 5,000 specimens, and it could take up to 3 years for us to work all the way through it. So I always need lots of help. So once you guys go to college at U of M, you can sign up with me to volunteer. So, any more questions?
I have a question for you. Is there a time that they could come if they're in Missoula?
Yeah.
Or a place to come to see you and see the T-Rex skull and some of the collection?
So that display area that I showed you a video of is open during business hours of UM. So 8 to 5 Monday through Friday, and then randomly on the weekend. So if you came to campus on a Saturday, you might be able to get in the building. If you contacted me ahead of time, I can let campus security know that there's people wanting to get into the display area on the weekend, and we'll make sure that that building is open. Now, if you wanted a guided tour with me, all you have to do is shoot me an email and let me know when you're going to be in town, how many kids, and I can give anywhere from an hour long to however long you have to look through the displays, look through the collection, and all of my contact information can be found online. hs.umt.edu/paleo is our website with all of my contact information.